What goes up must come down, at least in our everyday experience here on Earth. In a microgravity environment, like the International Space Station, the point is a little more moot. So, let's confine ourselves to earthly experiences. Virtually all energy on Earth comes from solar energy. That includes coal and petrochemicals too. They are mostly dead vegetation and even some animals. They all managed to exist because sunlight provided the necessary energy for plants to grow and ultimately feed the animals. One of the most common sources of energy is the weather, which only works because we have vast quantities of water on our planet. The sun heats bodies of water that evaporate into water vapor that rises and then falls as rain or snow in the mountains. It then runs downhill under the influence of gravity, carrying minerals and nutrients across the land, making other life possible. Sawmills, grist mills, hydroelectric generators, and everything that is powered by naturally moving water is powered by the sun and gravity. Water moving from a high place to a low place is a ready supply of power for humans. The first hydroelectric generator was built in 1879 at Niagara Falls. The falls are nearly 60 meters tall and pass 57 Olympic-sized swimming pools of water over the lip every minute. That is enough energy to power a quarter of the electrical requirements for Ontario and New York State. Of course, big powerful waterfalls don't exist everywhere. Humans built electrical generators all over the world once electricity became an essential for society. They had to be big enough to handle the maximum load expected. But what happens when the town is asleep? A coal-fired, petroleum-powered, or nuclear generator can't be turned off. Some take hours or days to get up to maximum capacity, and the same to shut down. Instead, we turn to power plants that can be started and stopped easily, those powered by natural gas. When demand peaks above the ability of the normal baseline generation to supply, those plants are started up in order to meet the demand. They may run for only as little as 2 hours per day, but they are necessary. Similarly, we use green power generators like wind, tide, and solar energy to supplement the grid. Unfortunately, in the US, only 12.6% of power is green because energy producers actively suppress it. They like the current arrangement and don't like the idea of alternative energy cutting into their profits. Fortunately, some companies, seeing the writing on the wall, are starting to invest in these alternatives as they foresee declining profits as their own services face more public pressure and regulation. Soon, the status quo will be a thing of the past. Pumped into hydro storage is a form of gravity battery. The first one designed was built in Switzerland in 1907. A clever engineer thought, we have a generator with enough capacity for our needs. If our needs were constant, if only we could store the extra energy it makes when we don't need it, and then use it later when we do need it. The answer was to build a reservoir uphill from a lake. When the generator was making excess energy, water could be pumped up to the reservoir so the generating capacity wasn't wasted. When the extra energy was needed, the water could be allowed to flow downhill and turn a turbine to make electricity again. It was an elegant solution and has been used all over the world ever since, wherever geography permits by having mountains. Renewable power sources are great. We have generators that are turned on by the tide a couple of times per day. We have solar collectors that provide power when the sun shines brightly. We have turbines that spin whenever the winds blow. The thing they all have in common is that they are not continuous. The future is always in flux, but two likely scenarios are fusion power becoming a reality in the next decade, or that we'll launch orbital solar energy collectors up where sunlight is much more intense and beam the energy back to Earth by microwave. We're on the verge of break-even fusion now with maturing technologies like Z-pinch confinement that gets rid of the superconducting magnets. However, that is not the point here. Until these technologies arrive, fully fledged and ready to power the planet, we have to cope with sporadic energy production on fairly unreliable cycles. That means we have to store energy for a rainy day using existing technology. Being able to store energy makes renewables possible. Mine. all mine. As an example, some ambitious people have proposed using old mine shafts if they happen to be conveniently located. It would be a simple matter to build a hollow steel cylinder suspended by cables in an abandoned, worked-out mine. That could be filled with loose rock and concrete poured from above. Electric winches could lower it to generate power and could lift it to store energy when there was excess generation. If it's very deep, that could provide plenty of gravitational potential energy. It depends on there being a mine nearby, of course. But it's another possibility, and creativity is important while looking for energy storage solutions. Crane power. One stunningly efficient way looks like a construction worker's nightmare, designed on exactly the same principle as construction cranes used for building office towers. This uses 3 such cranes. They are stacked vertically and extend equally in both directions. Using blocks of concrete that mass 23 metric tons each, one of the cranes raises 2 blocks at the same time, one on each end for balance. It uses excess electrical generation capacity to stack them around itself. It's not just a function of height, but layers too. If you need more capacity, simply utilize longer crane arms with more layers of blocks. It could look like an apartment building, or you could hide it behind hills or trees if the appearance bothered people. The lifting motors then function as electrical generators for when the blocks are lowered once again. The difference between this and pumped hydro storage is that water storage is about 70% efficient, which is very good, but this mechanical storage can be up to 90% efficient. An additional advantage is that this has a very small footprint for a town or city. The structure is just 60 meters tall, a demonstration unit, but it needs no more land area than a typical warehouse. One twice as tall at 120 meters or 390 feet would use the same space and be capable of storing 20 megawatts of power, or the daily energy requirements for 2,000 homes. You could have as many of these as required in a city. These require absolutely no brand new technology. Everything needed already exists, is comparatively inexpensive, and could last for half a century. Better yet, the entire operation could be run by automation, so you wouldn't even need people except for periodic inspections and maintenance. It would be a great companion piece for solar arrays and wind generators. Piston power. Another possibility is similarly straightforward and within our current capability. Imagine excavating a giant hole about 250 meters or 800 feet wide and equally deep. Line it with waterproof barriers and concrete for strength. Build a hollow cylinder within and fill that cylinder with all the material removed to make the hole. That is a piston with 12,250,000 cubic meters. Since soil and rock mass about 1.3 to 3 tons per cubic meter, that should be roughly 24,500,000 tons, or 23.6 million long tons and 26.4 million short tons. Now, if we simply pump water beneath this piston, we could raise it up by 250 meters, giving us an immense energy storage capability. In fact, such a piston could store 8 gigawatt hours of energy, enough to power all the homes in New York for over a month based on peak draw of 11,000 megawatts per hour, although it is usually considerably lower. It would take a long time to get to full capacity, of course. Some people have proposed much smaller, multiple pistons for more modest cities or towns. They could balance power demands at a moment's notice, eliminating fluctuations in the power grid. Ultimately, it all comes down to how creative we can manage to be. There are plenty of solutions to tide us over until we finally get limitless fusion energy or beam solar power from orbit to every point on Earth. Gravity batteries won't be the whole solution. No one solution will solve everything. Cars will need electrical power as we wean ourselves off polluting petrochemical fuels. Better car batteries are already on the way, able to hold enough energy to drive 3,000 kilometers before needing to recharge. That energy may come from gravity batteries, but you certainly won't fit a gravity battery in a car. What will happen is that no matter the source of energy, gravity batteries will almost certainly play an important part in that energy storage. The great thing is that gravity batteries work on existing technology, are inexpensive to build and maintain, and are just what we need right now. Let's do away with solar generators being shut down or wind turbines being stopped because we can't use or store the energy at the time of creation. Once we do that, we can get rid of these polluting power plants that we currently need to manage peak loads. And that makes for a greener and cooler Earth. And who doesn't want to be cool?